quick what I have here on the board. So I was looking at our calendar, and I've already like deviated from our schedule. Like I'm already all over the place on that schedule, which I always do in this class because I just like to do it a certain way. We're going to talk about quadratic functions today, which is going to require that you know some factoring. I'll spend a little time on factoring today just to make sure you understand how to do it. I will also introduce the quadratic formula, which I know a lot of you have seen before. And then next time we'll do more quadratics. Hopefully we'll wrap quadratics up this week. And then next Tuesday, I was surprised we actually have an exam. It's been a month since our first exam. So next Tuesday we have an exam, and that exam will take place right here in class, right? So paper and pencil. And I'll send out a review probably Thursday after class sometime because I need to see how far we get. And depending on how far we get, that's what will dictate what's on this review. But I do intend on the information from Thursday to be on this test. All right? So we want to make sure that if there are any questions on this stuff on Thursday, we're not going to meet again for me to ask you to answer questions. So you'd have to reach out, office hours, text me, call me. You've got my cell phone number on the syllabus if you're interested in getting something answered there. So that's the plan. Okay? Questions on the homework? What did you have?
So the second page?
Uh-huh.
I was confused.
The second page.
Yeah,
Let me take a look at it real quick. Is it a graph?
Yeah, it's the graph.
Yeah, let me see.
I mean, I did
Oh,
my best,
yeah.
but I was still confused by how to read it.
Trying to think. It's not going to be easy for me to project that. You know what? Can we do this? Stop me 10 minutes before the end, and then I'll try and project that graph, or I'll get up on the board and draw it. And just that way, if anyone else wants to talk about that one, we can. If anyone else or everyone else that's okay with it can go. That sound good? Okay, so I want to kind of lay out where we're headed, like big picture. Okay, big picture. So we started out when we were doing graphs. We started with lines, right? And then we started talking last class about functions. So the next several weeks in this class is going to be about functions. And there's a bunch of different types of functions that we need to know how to graph in this class. All right? So the first type of function that we're going to be working on, or that we already know how to do, is what's called a linear function. Let me put up here functions. Okay. Linear functions. Linear functions look like this. F of x equals mx plus b. A specific example of this, that's the general form. A specific example would be f of x equals, let's say, negative 4x plus 1. We should all be comfortable graphing this function, right? So the next thing we're going to do, all right, so that's check. We've already done that. The next type is quadratic. A quadratic function. After we do quadratics, we do, gosh, this is squeaky, polynomial, but it looks good. Okay, polynomial functions will come after that. Then we will study what are called rational functions. And then we will study what are called exponential functions. And then the last thing we'll do is study logarithmic functions. Okay, those are the 6 types of functions that a college algebra student needs to be exposed to. If you were taking the next class after this, pre-cal, which you're not, then you would be studying the trig functions, sine, cosine, tangent. You know, some of you may have seen that in high school. But this is what we're going to focus our attention on. The linear, by far, are the easiest to do, right? And so what we're going to learn, oops, sorry. I'm like looking for my phone. Sorry about that. Let me silence this. Okay, so what we're going to learn is that for each of these different types of functions, there's a different set of steps or procedures to sketch them. All right? And I would say out of all of these, the hardest is rational. That's the most complicated, confusing, tedious, long procedure. these problems can take 20 minutes to graph just one problem. So we're not there yet, okay, we're in quadratic, but this is kind of the layout of where we're going, all right? Each one of these functions serves a different purpose in the real world. Like a line, well, we talked about different types of things that are like lines. If you make an hourly rate, if you get paid hourly, you can graph like your income on a line. There's a lot of things that are linear. So each one of these has a special place in the real world. Quadratic, which is what we're going to study today, is really important, all right? We see it everywhere, even though you don't think you see it. So before we actually get into the process of graphing a quadratic and going through that, let's just talk about where quadratics appear in the real world, all right? Because sometimes if you know where they are, it kind of motivates your wanting to know about them. So I'll start with one of the most basic examples of a quadratic, and that is, let's see, I need a volunteer. You want to volunteer? Sure. Okay, you don't have to be on camera, but can you stand over there? Yeah. All right, let's try not to hurt ourselves, all right? We're going to try not to hurt ourselves. You're just going to stand there, and we're going to throw something back and forth here, all right? So we're going to throw this pen through the air, and I just want you to pay attention to the path of the pen, all right? So go ahead. Okay. All right, y'all see it? I mean, it looks like an arc through the air, right? How's it going? All right, so I'm going to get a little closer to you. All right, so if I go like this, that's still like this shape, right? Okay, that's good. Thank you. All right, so that shape through the air is special. It's not a circle, okay? It's some sort of arc. It turns out that the shape is called a parabola. And a quadratic function is exactly that shape, okay? So anytime you take any object, okay, here's me, you take any object and you throw it through the air, okay, then this shape here is called a parabola. Obviously it's not a line, right? It's not a line. But it's also not a circle. Like if you draw a circle, it's not this, okay? It's something different than a circle. And what's useful about this is that if there turns out to be some function that would draw this, right, then mathematically we can start to understand where things are if you throw them through the air. So I can just throw a rock and big deal. But if I understand the mathematics behind it, I can actually predict where that rock is going to land. And I can also predict how high it's going to go if I understand the mathematics behind it. Does that make sense? Now, where would that be useful? Well, back, if you look at history, this is a castle, right? That's a castle. Thank you. Thank you. So that's a castle, right? So if you look at history, right, you have people that didn't like these people, right? And they wanted all that shit in the castle, right? All their gold and all their food and all their stuff. So, right? So they're going to storm the castle. Well, to storm the castle, they're going to have to launch things, right, into the castle. And they want to not just be like this and like this and like that. They want to put things exactly in here, right? So if you understand the mathematics behind that trajectory of the object, if there's a quadratic function that dictates what's going to happen, then you can be very precise, right? You can be very precise. And obviously we've gotten better at this, right? Because even like modern day artillery, we can put a projectile, you know, in a small square miles and miles away because we understand the math behind it, right? Now, usually we use a computer to do all that, but that's one usage of a parabola. So, you know, I always tell my students, the fact that, you know, humans, that we don't get along with each other, right, that we like to fight, has pushed science and technology, right? That really has been a motivating factor behind progress, right? You have nuclear weapons were a result of World War II, right? We were pushing to see if we could figure out a way to make a big bomb, right? What about the internet? You all know where the internet came from? No? Would y'all like to know where the internet came from? Yeah. The idea behind the internet? So the idea of the internet is this. And this actually goes back to, this is the United States of America, so sorry if you don't like that. Okay, so the internet goes back to the Cold War, which is kind of ironic because we were talking about Russia before class. The former Soviet Union, I don't want to get too far into history here. World War II, Germany, Blitzkrieg goes out, right, all that. And then you had basically Soviet Union, Russia, and the United States and the Allies, and then we basically squeezed Germany back into Germany, right? And then when we got together, we were like met in Germany, and we don't get along, right? Communism, democracy. And so what happened was after World War II, we had this huge fight with the Soviet Union, but it was more of like like, how would you describe it? It's kind of like two guys bucking up to each other at a bar. You know, like no one was throwing punches, but everyone was ready to throw punches, right? So like a standoff, yeah. And it was a nuclear standoff. We had nuclear weapons pointed at each other. Kids in grade school would have nuclear fallout drills where they'd get under their desks in case nuclear bombs came. You know, it was very tense time back in the 60s. So the fear was this. Here's Soviet Union over here. The fear was this. They had all these nuclear weapons pointed at us, right? And we had all of our nuclear weapons pointed at them. And the way that we controlled the weapons was through these central locations. I think there's somewhere in like Colorado, I believe, there's a bunker buried deep in a mountain where we had central control. And then there's like a couple of different bunkers. And so if we detected missiles coming, we would launch everything, okay? And basically, right, and that'd be the end of humanity, pretty much. And they had their central, you know, locations where they would command and control everything. So the fear was that they wouldn't launch these, but they would somehow infiltrate and take these centers out. And so they would take this one out and break the communication with that one and break the communication with that one. And once they knocked out these central locations, then we wouldn't be able to launch a counterstrike. And so we said we needed a communication system that couldn't be debilitated with 1 or 2 or 3 bombs. We need something that would be like a spider web. And so even if you knock out part of the web, the rest of the web's there. And so they said, let's use our phone lines, right? Because the phone lines were already webbed all throughout the country. So that's basically the idea of the internet, was just let's use all this infrastructure that connects us all together, and that will be our communication, and then you can't knock it out. And so that's where it all kind of came from. And now, you know, we've replaced the telephone lines with what we're going to like fiber optic now and things like that. So, but it's still this big web. So that's where the internet came from. Okay, I'm going way off. Okay, so there's one example, the bomb thing, or the projectile is one example of parabola. Let me do one more. I have like 10 examples, but I'll give you one more that I think is useful. So you're watching a video in my class, which I don't appreciate, number one. I'll just say that right now, okay? But it's amazing that you can, right? So what's happening is that your phone is sending out signals, right? Right, all over the place. These signals are going out, right? And so here's you sitting in class, right? And then your phone right here is sending out signals in every direction, right? They're bouncing off the wall, they're all over going out the window, through the walls. And somewhere around here is a tower, right? You're probably using the Wi-Fi, right? But let's say you're just out in a field somewhere. There's a tower out here, and in these towers, they're all over town. They look like this. They have these little like rectangle boxes on them. What you don't realize is inside there is this shape. It's a shape like it's a parabola. It's not a half circle, it's parabolic. And what happens is it acts like a big ear. And any electronic radiation that bounces into it will bounce to a single point. No matter where it comes in, it will always reflect to that single point. Right? So no matter where this stuff is coming from. And that point is called the focus of the parabola. And so what it does is it amplifies the signal. The signal is captured, and then this tower will capture that signal in the little parabolic receiver, and then it'll send it out to another tower, and then to another tower, and then down to the other person maybe you're calling or texting. And it all happens at the speed of light, right? So if you didn't have a parabolic shape here, you couldn't capture this stuff. You have to be able to capture this stuff. That's what a satellite is. Satellite's the exact same thing. You've seen pictures of satellites that look like this, or even if you have like DirecTV, you have a satellite on your roof. Same idea, it's a parabolic. This has to be a parabola though, it can't be a circle, it has to be a parabola. So you capture that information. We wouldn't be able to communicate with each other, right? We wouldn't be able to use our phones if we didn't have parabolas. Okay, I'm gonna leave it alone. Your headlights, if you've ever used a flashlight where you can turn the end of the flashlight and the beam goes narrow and wide, that's all parabolic, mirrors and stuff like that. So quadratic functions are important, all right? So what are we gonna do with them? Our main goal, I give you a quadratic function, you draw me the picture. That's the main goal, all right? So here we go, formally, quadratic functions. Okay, so what is a quadratic function? A quadratic function is any function that looks like this. A, x squared plus b, x plus c. So a, b, and c here are just numbers. A, b, and c are just numbers. Golly, I'm sorry, this is so squeaky. A, b, and c are numbers, and we have one other condition. A can't be 0. Does it make sense to you why a can't be 0? If this number was 0, right, then that wouldn't be here, and then you'd no longer be quadratic. You need some number other than 0 in front of the x squared. All right, so that's what a quadratic function looks like generally. Now, this is called the standard form. Standard form of a quadratic. Okay, that's called the standard form. There is another form of a quadratic that looks like this. It's just another way to write a quadratic, and it looks like this. A parentheses x minus h squared plus k, and this is called the vertex form. The vertex form of a quadratic. And I'll talk more about this one later. For now, I want to put it on the board, but we're going to focus all of our attention today on this. All right, so let's look at what does a quadratic function like that, what do they look like? And I've already kind of alluded to this. I'm going to erase this. So all quadratics look like one of these two. Okay, it either looks like this or this. These are the two options. So the first option is that your parabola looks like a U here, like this, and it opens up. This is the other scenario where it could open down. Okay, so this we would say opens up, and this one opens down. Now I know some of you have a background with this. Can someone here tell me what in this formula dictates which of those two it is? Does anyone know? There's something about these numbers. There's a number in here. One of these numbers will tell you what it's doing, one of those two. Anyone know? It has to do with A. That's right. This number right here can't be 0, right? I already said it can't be 0. So it's either a positive or a negative number. If it's positive, it opens up. If it's negative, it opens down. So this will happen if the A we have is positive, and this will happen if the A is negative. You can think of it this way. This looks like a smile, right? Positive people smile, right? Negative people frown. That's the way you can remember it. Okay, so all quadratics are going to look like one of these two, and it's dictated by this and this only, all right? That's the first thing. The next thing, I'm going to leave that right there. Let me move this up a little bit. I want us to talk now about some of the aspects, characteristics of a parabola. Now, I could draw either one of these right now, right? I could draw either one, but I'm going to just use this one right here, okay? So let's say we have a parabola that goes like this. Comes down, comes back up like this. Whenever you have a parabola, okay, the lowest point on the parabola is called the vertex. And we usually give it an x and a y coordinate. But we don't write xy, we write hk. So h is how far you move over here, and k would be this number, right? Go over h, and then whatever k is, that's where you move up or down. Depends on the parabola. So the vertex, let me say it this way. If your parabola opens up, your vertex is the lowest point on the parabola, right? But if your parabola opens down, your vertex is the highest point on the parabola, right? It just depends on which way it opens. So the vertex is either the lowest or the highest. Now, the other thing about this vertex that's important is to know that if you were to draw a vertical line right through the H, okay? This right here is what we call the axis of symmetry. It's so squeaky, I'm sorry. I don't remember the board being this squeaky. The axis of symmetry. And what we mean by that is when you look at a parabola, and my parabola does not look very good, the axis of symmetry is saying that for all parabolas, if you draw this line right down through the vertex, vertical line, then if you were to reflect this side of the parabola over, it would land right on top of the other side. So the parabola should be a mirror image of itself over this line, which means your parabola shouldn't look like this. Like that's not a parabola, because can you all tell that doesn't look like a reflection, right? So when you draw a parabola, once you determine the vertex, you should always think that it's going to look like a mirror image of itself over that dotted line. Make sense? Okay, let's keep moving. I want to draw more pictures here for you. So we have the idea of up or down dictated by A. We have the idea of a lowest point or highest point, right? And then this axis of symmetry. The next thing I want to talk about are x-intercepts. Let's talk about the x-intercepts for a parabola. And actually, I'm going to ask you, how many x-intercepts do you think a parabola has? What do you think? 2? Okay, so like this picture here, right? If I draw a parabola, it looks like this, right? Does everyone see I have 2 x-intercepts? 2 x-intercepts, right? Now, is that the only case we could have? What else could we have? You could have none. None would look like this, right? No x-intercepts. Why did I leave that one blank? How? The down one, yeah. So if we were drawing down ones here, then I could draw a down one look like this. Then it would have none, right? Or over here, if I were drawing a down one, there's an example of 2 x-intercepts, right? So there's 2, there's none. Is there any way to have just 1 x-intercept?
Just hits the x-axis.
If the vertex is the point that hits the x-axis, then you would have 1. Okay, so we can have this happen, right? And if we're talking about ones that go down, then it would have to be, doesn't matter where I draw it, just as long as it hits it once. So I hope this makes sense. The purple ones are examples of parabolas that open up, and give you 2, 1, and none. The red ones are examples of parabolas that open down where you would have 2, 1, and none. Make sense? So when it comes to x-intercepts, we need to understand that we're going to have one of three things happen. We're either going to have no x-intercepts, one of them, or two of them. All right, what about y-intercepts? What about y-intercepts? Look at these. Look at this graph right here. How many times do I hit the y-axis? This purple one right here. How many times do I hit the y-axis? Once, right there. How about this red one? How many times does it hit the y-axis? Yeah, this goes on, right? This goes on and on and on. So I'd hit it eventually here, right? Once. How about this purple one? It would eventually hit right up here somewhere. So I'd have one from this one somewhere up there. And then this one, there's one right there. This one would eventually hit, right? Somewhere up here it hit. And then this one right here would eventually hit. So we would have, in all of these cases, we only have one y-intercept. Y'all see that? There's no way to draw a parabola. There's no way to draw one of these functions that opens up or down and have it hit the y-axis more than once. It has to hit once. Okay? So we're guaranteed one y-intercept. So x-intercepts, we can have 1, 2, or 3. But when it comes to y-intercepts, there's always one. Recap. Given a parabola, the A tells you if you open up or down, right? The vertex is either the lowest or the highest point. Axis of symmetry. You have a question? Thank you. 1, 2, what do I mean to put here? 1, 2, or none, right? 0. Let's just do it this way. Yeah, I like it. 0, 1, 2. Thank you for paying attention, sir. X-intercepts, we can have none, 1, or 2. Y's, we have to have 1. A tells us up or down. Vertex is lowest or highest point. Axis of symmetry, right? We can have 0, 1, or 2 x-intercepts, and we have to have one y-intercept. Okay? Questions? So now what the whole idea now is, I want to be able to give you a function and for you to sketch it. And so for you to sketch it, what you're going to do is follow a procedure. You're first going to find the vertex. After you find the vertex, you're going to go find the x-intercepts. After you find the x-intercept, you're going to find the y-intercept. And when you do all that, you'll be able to draw a picture. All right? That's the general idea. Now I need to get to it. Or I need to actually, there's a lot more to it than that because we're going to run into some problems here. So now is I'm going to put here the steps to sketch a quadratic function. All right? This is probably the most important thing for us here. The steps to sketch a QF. I'm going to say QF for quadratic function because I don't feel like writing it over and over. Okay? So here are the steps. Given some function f of x equals ax squared plus bx plus c. So if we're given the quadratic function, the first thing we're going to do is determine if it opens up or down. Okay, that's the first step. That's the very first thing we need to do is determine if it opens up or down. Now, to do this, all we're going to do is this. If A is greater than 0, it opens up. If A is less than 0, it opens down, right? That's all we have to do for the first step. Just look at what A is, and that will tell you that, right? Okay, the second step is we're going to find the vertex. Now, I have not told you how to find the vertex, have I? I just told you that every parabola has a vertex. But to find it, we have to use a formula. And the formula actually comes from calculus. So it's a gift from the calculus class. In calculus, they figure out a general way of finding the vertex of a quadratic. And then in this class, they just provide you the formula. Like, here's the formula, okay? Go use it. So we're not going to talk about where it comes from. You're just going to say, okay, great. So remember, the vertex is a point, right? There's an h, which is the x-coordinate of the point, and there's a k, right? That's what the vertex is. So what we do to find the vertex is we use this formula. First of all, h will always be equal to negative b divided by 2 times a. Okay, so look at this formula, negative b divided by 2 times a. What do I mean here? I mean, look back up here, right? You'll know what your a, b, and c are, right? You will take the opposite of whatever b you have. So like if this number was a 4, this would be negative 4. If this was negative 4, this would be positive 4. So you're always going to take the opposite of the b on top and then divide that by 2 times the a, so twice this number. That will always give you this x-coordinate of this point, all right? Now to get k is the hard part. To get k, what you have to do is take that answer you just got and plug it into the function. That's what this means. So let me explain. Let's say you go and find h, and let's say h turns out to be, you do all this and it turns out to be 2. Then what you're going to do is take 2 and plug it into the function for x. And whatever that answer is k. I'll do an example, but this is the procedure. You take that answer and then evaluate this function. Plug that number into the function. If you mess up h, k is going to be wrong as well. Right? As soon as you mess up h, this is going to be automatically wrong. So you have to be, just be careful on that computation. All right. Let's keep going with the steps, okay? That step 2 will become more clear when we actually do an example. Okay, third step. Now, I'll just warn you now that if you've seen how to sketch a quadratic function in the past, or if you wind up in the tutoring lab or something, or you go ask your friend who's taking college algebra how to sketch a quadratic function, I can pretty much guarantee you that they don't do this step, okay? This step is a step I like to do because, well, hopefully I can convince you why it's a good step, all right? What we're going to do next is we're going to do a quick sketch. A quick sketch. Now, you'll see why. You'll see why when we do an actual example. What's going to happen when we do a quick sketch is that this step will tell us how many x-intercepts we have. Okay? When we do this quick sketch, off of we have only 2 things, we only